Dr. K. Parinivelu, Professor at the Center for Environmental Studies and Director of Center for Climate Change and Disaster Management, Anna University, Chennai. He obtained his PhD degree from Indian Institute of Technology, Madras, Chennai. He worked as project officer for a brief period at IIT Madras and moved on to the Center for Environmental Studies, Anna University in 1992. He was a visiting professor at Chungam National University, South Korea during 2007. He has been teaching courses on environmental chemistry, environmental pollution control, and instrumental methods of analysis since last 27 years. He has guided 75 students for ME and MSc, 4 MPhil, 2 MS, and 15 PhDs. He has published 135 papers in journals and 90 in conference and symposiums. He has received several awards in national and international levels.
Welcome to the lecture series on environmental chemistry. The previous classes we discussed about atmospheric chemistry and air pollution, and from today we are going to start the next unit on aquatic chemistry and water pollution. Water, all of us know, one of the essential things for human life and other animals as well as aquatic plants, and the health of the environment generally. A healthy environment usually is one of the one in which the water quality support a rich and varied community of organisms and protects public health. Clean fresh water resources are essential for drinking, bathing, cooking, irrigation, industry, and for plant and animal survival overall. And nowadays water is becoming a precious and scarce resource in many parts of the world due to two reasons. One is quality because of pollution, and the other one is availability of the water, that is water availability quantity due to climate change. So water has two dimensions that are closely linked, that is quantity and quality of the water what we are going to use for our various beneficial uses. As I mentioned before, the water availability is a question mark because of climate change issue. Many places throughout the globe water is becoming scarce, and many part of Africa there is a zero water day is being observed, that is water is given in ration. That's because of climate change. At the same time, many part of the globe water is polluted because of the pollution due to discharge of untreated effluent reaching the river, stream, and other freshwater system, ultimately polluting this, and because of this lot of health related issue also happening. Generally water we refer it as a hydrosphere, and this is a term collectively given to all different forms of water. That is, it includes all type of water resources such as ocean, sea, river, lake, streams, reservoirs, glaciers, and groundwater. Everything put together we call it as a hydrosphere. And the hydrosphere is a layer of water that in the form of ocean covers approximately 70% of the earth's surface. Okay. Whatever earth's surface available, nearly 70% is covered by ocean, sea water. And water occurs in all spheres of the environment, that is in the ocean as a vast reservoir of salt water, on land as a surface water, and includes lakes and rivers, and as well as underground water, that is water available below the ground, as well as in the atmosphere as water vapor. Whatever water evaporation takes place from this sea water as well as surface water, ultimately reaching the atmosphere, there it is available as a water vapor. As well as considerable amount of water is also available in the polar ice caps as a solid ice. So everything put together forms a hydrosphere, that is what available. And this diagram clearly shows the whole globe water supply available, or what is available. As I told you, 97% is covered by sea water, mostly not directly useful for us for direct consumption, and 2%, about 2% of water is available in ice caps and glaciers, and 0.6% is the groundwater, and 0.01% in the surface water as well as in moisture, and the atmosphere moisture also contains about 0.001. So, if you see about 1% of water only available as a fresh water that is fit for human consumption, and 2% it is locked in polar ice, and nearly 70% of the water available as in the sea, which is not directly. So, in the 1% of water only we have to manage for our various purposes, and as I mentioned before, the water availability is becoming a very serious issue nowadays because of climate change. And we know, especially in summertime, the well is dry, we know the wealth of the water. Till that time we use the water very without any care, I can say, and we realize the importance of water only in summertime when water is not available. So, the water is getting cycled in the various spheres of the environment, okay, and this diagram shows how it is happening. Clearly, the main process are the atmosphere, and here ocean and fresh water, and water is getting evaporated from this fresh water as well as ocean and goes into the atmosphere. There at a favorable condition, what happens is it comes return in the form of rain. Okay. So, transportation from water is taking place from fresh water and the sea into the atmosphere, where it acts as a condensation unit, brings rain, which is again get distributed. So, everything different route it is happening. The moment it comes to the earth, even water percolates and goes into the groundwater, and to the soil also water is available, and considerable amount of water is available at the soil moisture in the topsoil also. So, this completely shows you the how the water is getting evaporated, percolated after rain, all those things is explained. If you see the importance of water, as I mentioned before, it is very essential for all living things, and this is a medium from which life evolved and in which life it is also exists. Water is a very important component, and water carries energy and matter through various spheres of the environment. Through water it is happening, and water also leaches soluble constituents from mineral matter and carries them to the ocean, or leaves them in the mineral deposit some distance from their source where it is available. So, water acts as a leaching fluid here and solubilize that and carries to different part, and that includes even nutrient, plant nutrients also, from soil into the bodies of the plant by way of plant roots it is happening. And also it absorbs solar energy available in ocean water and release the latent heat when water evaporates, that provides the energy that is transported from equatorial region towards Earth's pole, and that is responsible for the massive power of the storms. So, the latent heat of solar energy release by absorption, the water is actually turning into the storm with the power one. And water we very much require for different uses, and this slide shows you what are the major usage of water. See, roughly about 30% irrigation, it is used for irrigation. Industrial uses it is about 13%, and only about 7%, less than 10% we use it for domestic purposes, and nearly 50% of water used for thermal power plant cooling purposes. Okay. So, this is a rough one, but there is a slight variation may be there depending on how we use it. So, if you see this major water usage, it is a thermal power station and agricultural purpose, nearly 3/4 they use this water for this. If you look at the properties of water, and before going to the properties of water, water is believed to be formed by the chemical neutralization reactions. That is, we all know when acid reacts with alkali, forms salt and water. Through this process only, the entire water is formed, and especially in the volcanic and whatever acids released from the earth might have reacted with the volcanic ash, mainly contains calcium, magnesium, all those things, and they form the salt, and ultimately leaving the water. Through this process, water might have been formed. And now if you look at the properties of water, water is a dipolar molecule. The electronegative oxygen with a negative charge and hydrogen with a positive charge, it acts as a dipolar and with a good dielectric constant and dipole moment about 80, and this is a universal solvent. Okay. Water is considered as a universal solvent, dissolve most of the materials in it due to this dipolar nature. That is, polar nature, especially all polar compounds are very freely water soluble. And another property of water is hydrogen bonding. That is, water has the ability to form hydrogen bond between the partially positively charged hydrogen atom on the one water molecule and atoms in another water molecule, that is a negatively charged oxygen atoms in another water molecule. It is believed one water molecule is surrounded by 4 water molecule, another water molecule in this way, and water behaves as a tetrahedron structure. And hydrogen bond formed in this way holds water molecule together, but the strong and also help to hold some solute molecule or ions in solution. That is, it explains the solubility for certain compounds. Again, the hydrogen bond of the water helps in this. So hydrogen bond is also responsible for its viscosity, surface tension, all those things. And water, we all know, evaporates at 100 degrees Celsius and freeze at 0 degrees Celsius. Okay. These are some common properties of water. But coming to chemical property or chemical reaction in water, that is what very important as a environmental persons. Okay. And some of the chemical reactions in water bodies, what is taking place are solubility of gases and solid and liquid. Okay. This is one of the major things, because water is a medium, lot of pollutants are there released into the water bodies, and ultimately that causes a pollution. So, the solubility of different chemical substances in water is one that also we will have a look at it. And then acid base reaction in water, redox reaction, that is chemical oxidation and chemical reduction in water, as well as complex formation with the different metal ions in water. All these things are peculiar to water. This slide shows you the various chemical processes taking place in the aquatic system. Exchange of gases is happening. Oxygen from the top of the surface may be exchanged into the atmosphere. Similarly, carbon monoxide, if it is present, that is getting exchanged, one reaction. Another type of reaction is redox reaction. Suppose nitrogen is present, that on the bottom part it may be reduced to ammonia, and in the top part it may be present as a nitrate or nitrate. That is possible. And again, photosynthesis in the top part, especially where light is available, carbonate or bicarbonate present are converted into organic components. Then acid base reaction, carbonate may be converted into acid under certain conditions into bicarbonate, vice versa. And if carbonate is present, that may react with the calcium present in the water, gets precipitated as calcium carbonate, precipitation reaction. Microbial oxidation, organic compounds may be converted into carbon dioxide. And then chelation, chemical chelate formation with metal ions like cadmium is there, naturally occurring ligands may form complex with this. Also, water is in touch with the sediment, so there is a possibility of certain compounds get leached, especially water soluble compounds gets leached from sediment into the aquatic system. At the same time, it is also reverse reaction, that is, some of the water soluble components may be converted into water insoluble compound that gets precipitated as a sediment. For example, if sulfide is present more, this sulfide may react with certain metal ions, form insoluble sulfide and get deposited thing, and favorable condition as calcium carbonate. So all type of chemical process is taking place in the water. We will see certain reactions happening in detail. First, let's say acid base equilibrium. So the pH, normally acid base equilibrium is represented by pH, that is the relationship between hydrogen ion and hydroxide ion present in water. Water itself produces both H plus ion and hydroxide ion, that is, it is a very weak material. Its dissociation constant is pKw value, that is 14, or Kw 10 power minus 14, that is the dissociation constant, and ultimately it leads to formation of H plus ion and OH ions, and the Kw value is 1 into 10 power minus 14 at 25 degrees Celsius. So that means water provides acid and alkali, H plus and OH in water. And we know acids like hydrochloric acid, sulfuric acid or nitric acid, they produce H plus ion in water, which are all very powerful strong acids, considered as a strong acid. And the concentration of H plus ion is usually measured by pH, that is represented by negative logarithm of H plus. And the pH scale vary from 0 to 14. 7 is considered as a neutral, below 7 it is acidic, above 7 it is alkaline. Okay. We have seen some strong acid, at the same time we have weak acid also likely to be present in the aquatic system, like acetic acid. At the same time, water also may furnish hydroxide ion. If sodium hydroxide and calcium hydroxide there, they produce hydroxide ion in water. These are all strong alkali. Okay. And also it may be present, like ammonia is present, which is considered as a weak base. So we have in aquatic system both strong acid and alkali, at the same time weak base and weak alkali, they are all maybe in aquatic system. If it is neutral, the water, it is the concentration of H plus and hydroxide ion is equal, and that is 1 into 10 power minus 7 moles per liter. This solution is considered as a neutral and pure water it is possible. And generally these acid and alkali will be in equilibrium in water, and many of the phenomena in aquatic system and as well as geochemistry involve solution equilibrium, that is with respect to acid and base. In a general sense, solution equilibrium deals with extent to which reversible acid base or other reactions such as solubilization, that is precipitation also, complexation, oxidation redox reactions, everything as I discussed is governed by chemical equilibrium concept. That is, it can proceed in a forward reaction, under favorable condition it can be reversed also, that is backward reaction. And this can be generally expressed by the generalized equation. Suppose two reactants A and B react to form C and D. This is in equilibrium. Suppose we alter the equilibrium by somehow, and the system will adjust in a such a way that it try to maintain the equilibrium as per the Le-Chatelier principle. So if you consider a weak acid like acetic acid, it will also undergo ionization, and the ionization reaction can be represented by like this. Acetic acid will dissolve in water to furnish H plus ion and acetate anion. The acetate anion structure is represented by this. Okay. And if you write the chemical equilibrium equation, it is like this: acid concentration into acetate anion concentration divided by the undissociated acid of acetic acid. The dissociation constant value at equilibrium is 1.75 into 10 power minus 5 at 25 degrees Celsius. Okay. So this value is a dissociation constant, and the value at 25 degrees Celsius is constant. Suppose we alter by doing this, the value will not adjust, but the other concentration, either acetate anion or H plus or acetic acid concentration, will vary accordingly, try to maintain the equilibrium value. These are the various weak acid ionization constant that is normally available in the literature, and these values are very useful, the corresponding dissociation value and the pKa value. For acetic acid it is 4.75. Okay. So, like this various type of reactions are happening here. Similarly, carbonic acid also, it undergoes dissociation to form bicarbonate as well as carbonate, and the pKa values are 6.37 and 10.33, like this. Okay. So, different type of weak acid undergo dissociation to furnish this, and these values are available in literature, very useful, and the abnormal significance is also indicated, whether it is for disinfection or organic waste treatment, nitrification, or other applications like that. In connected with acid base equilibrium is the main concept is buffer. Okay. This is very, very important, especially for biochemical reactions. What is a buffer? That is the solution, that is aquatic solution, that resists changes in H plus ion concentration, are usually called as buffer solution. That is, the pH will not vary very much by the small addition of acid or alkali. That is, the reasonable quantities of acid or alkali added, that is dilute, to such solution do not cause large change in H plus ion concentration. Okay. For the small addition, we should not add sulfuric acid to water, then it becomes a sulfuric acid solution, not a buffer solution. So, it is only for small addition or generation. Certain material will resist the change in pH value, that solutions are called buffer solution. To act as a buffer, what type of things are available or can be used as a buffer solution? And usually these buffer are mixture of chemical, that is weak acid and its salt can act as a buffer, or a weak base and its salt can act as a buffer. That is, they keep the H plus ion concentration of a solution relatively constant. How? We will take one example and see. Acetic acid and sodium acetate, that is salt, can act as a buffer in acid medium. If you consider acetic acid, the solution is usually present as a undissociated acetic acid, because being a weak acid. The H plus, which is in solution, is therefore, because a very small amount of acetic acid has a dissociated to H plus and acetate ion. Being a weak acid, it will undergo dissociation. Okay. The sodium acetate is represented by sodium ion and acetate anion. Okay. It is a salt of acetic acid. If some base such as sodium hydroxide is added, let us assume now, what happens is some of the acetic acid present in a solution will react with this sodium hydroxide, that is, it takes up the hydroxide and gets converted into sodium acetate anion and water. Okay. Water is formed, which is again a very, very weak electrolyte. Okay. So, the weak acid, for the addition of small amount of hydroxide, is converted into water, and it is the salt is sodium acetate is formed. This is how, for the small addition of alkali, how this acids react. Similarly, if you add a small amount of acid to the solution, like a hydrochloric acid or some other acid, small addition is happening, this H plus will react with acetate anion and gets converted to the weak acid, namely undissociated acetic acid. So, this H plus is taken up by this and gets converted to weak acetic acid. So, in both the way, this acid or alkali added to the system, the sodium acetate acts as a buffer, neutralizing or resisting the change in pH. And usually the pKa value, what we have discussed before, is a thumb rule for pH maintenance. plus or minus 1. For example, acetic acid 4.74 is a pKa value. So, plus or minus 1 range we can use them as a buffer mixture. So, not only acid, a mixture of a weak base and its salt also can be used as a buffer solution at the corresponding pKb value pH. For example, ammonia and ammonium chloride can also act as a buffer. Okay. And similarly, mixture of two salts can also be buffers like this. In the example, monosodium dihydrogen phosphate and disodium monohydrogen phosphate, these are all salt, but to act as a buffer, at least one free hydrogen H plus ion should be available. Such type of salts can be used as a buffer, and mostly phosphate buffer is what that is available inside our body fluid. Our body fluid is made up of phosphate. Such type of phosphate compounds act as a buffer to resist the change in pH value, and this can be converted into a very useful relationship between pH and pKa value. Okay. By taking logarithms to the base 10 of the above equation, this can be converted into this form. Okay. This K, this is the equilibrium value. By taking logarithms, this equation will appears like this in acid form and anion form. So, the equation is given here, in which the acid is concentration undissociated one, top it is the anion. Okay. And the modified equation, this one, whatever the conjugate base and acid, or conjugate base and thing. So, considering acetic acid as it buffer containing 0.1 molar acetic acid and 0.05 molar sodium acetate, let us assume, and if we put this value concentration in the Henderson equation, the pH of the solution will work out to 4.4 as per this one. Okay. That is the salt concentration divided by the acid concentration. If you solve this, the pH of this equation will come to 4.4. This explains how this pK value or pKb value of acid and bases along with the salt concentration can act as a buffer. So, the combination of acetic acid and sodium acetate is there. If you add sodium hydroxide to this acid mixture, and hydroxide ion will react with the acetic acid, gets converted into water and sodium acetate. So, the hydroxide ion added is getting neutralized in this way. The pH will not change drastically. Similarly, the sodium acetate combination buffer, suppose little hydrochloric acid H plus is added, the acetate anion will react with this H plus and gets converted into very weak acetic acid, thus neutralizing the acidity of this reaction. So, in this way, both addition of hydroxide or H plus, this combination of acetic acid and acetate will act as a buffer. So, to summarize this lecture, we have started with seeing the importance of water, what are the properties of water, various chemical reactions taking place in brief you have seen with the acid base equilibrium in detail. Remaining thing we will continue in the next class. Thank you.